This is the video solution set to Week 5's academic conference. As you can see on the screen, I'm looking at the question set here. It's about concerns Burger's Bagels and their hot chocolate. It says that Burger's hot chocolate tastes best at 142 degrees Fahrenheit. And to test the temperature of their hot chocolate, the quality control sampled 24 cups at random. And if the sample data results leads quality control to conclude that the temperature of Burger's hot chocolate is different from 142, and different being capitalized is meaningful, then they will have to recalibrate their machines. So we assume the population is normal. We have a small sample, so that's implicit there. We have to make that assumption and use the data attached in a 0.05 significance level to test whether Burger should recalibrate their machines. In other words, to test whether they find that these things are indeed, that the hot chocolate's indeed different from 142 degrees Fahrenheit on average. And we're going to use the t-distribution in place of the z. All right, and to reiterate what the book and the modules are saying is that you're going to use t when you have small samples, okay, less than 30, and you don't know the population standard deviation. So you don't have a measure for sigma. You'll have a standard deviation from the sample, S, but you won't have a population parameter measure. And so when you have those two situations, you're going to use T. And that's where we are now. So let's open this data set. It's pretty straightforward. And I'd like to take a minute to write out the appropriate null and alternative hypothesis, which should be formulated in the following way. You always start with the alternative, and the alternative is your research question, right? And the research question was whether the average, and that's mu, temperature was something different from 142 degrees Fahrenheit. All right? And when the alternative is different from, then the null hypothesis is equal to, right? This again is the null, and this is the alternative. All right, but the alternative is your research question of interest, which sometimes can be confusing. So when I capitalize different from, that is what is driving me to formulate the alternative like that. We're also going to use a 0.05 significance level and a t-distribution. I know that the t-distribution is a fairly normal distribution, becoming closer to the standard normal as n increases. But in any event, the picture of this test is going to have a rejection region on either side. Right, we're concerned both if the temperature is too hot or too cold, and that is 0.025 on each side. Okay. We can also add the x-bar axis here, which is centered at the hypothesized value. Okay, so I have a t-axis, which is a standardized axis, and an x-bar axis. And my shaded regions are rejection regions. So what I need to conclude this test, okay, is there are a number of ways I could do this, but I need to compare my test statistic to my critical value. Okay, my critical t value, which I'll call t crit right there. So the test statistic follows, that's a subscript stat that I'm using just to indicate that this is a test statistic, is you're going to be your sample mean minus your hypothesized mean, which is 142, over the denominator, which is the standard error, and this S is the sample standard deviation, and this is the sample size, which is 24. Alright, so we already have a few elements in here. This is 142. But we need to know what our sample mean is and our sample standard deviation to fill out the rest. And a quick way to do that is to go to this data analysis tool set in Excel and click Descriptive Statistics. Highlight the column of data and click Summary Statistics. I also clicked Label in first row because I did select the label of temperature in degrees Fahrenheit. And I can include actually my confidence interval for the confidence level for the mean at 95% is appropriate too. I'll show you what that does. Hopefully my work is saved on the other side. But this is nice. The output from Excel's summary statistics, which is kind of nice. If you look at this, okay. You'll see that the mean is calculated right here. So my sample mean is 141.375. So that's what I'd plug in right here. Right, so the numerator of my test statistic is the absolute difference between a sample mean and a hypothesized mean. Okay, so that's simple enough. And then the denominator just standardizes it. And again, the denominator s divided by the square root of n is what's called the standard error. So this is already calculated for you. So this thing together is 0.4074. Now I could calculate it individually by taking n, 24, and sample standard deviation, 1.99, and just taking 1.99 and dividing by the square root of 24. Anyway, if we do this calculation, let me grab my calculator. Well, I could just use Excel here since I'm obviously. T-stat is going to be a numerator of 141.375 minus the hypothesized value of 142 divided by 0.4074. So negative 1.53 is my test statistic. Now to get the critical values, I want to go to my t-table. Let me pause this and I'll bring it up. Alright, so here's the t-table. If you note, the degrees of freedom are going to be n minus 1, so 23 degrees of freedom. So that's the appropriate row. And the appropriate column is going to be alpha divided by 2. And here is that appropriate column, so 2.069 is the critical t, and I'm going to have positive and negative values of that. So 2.069, let's go back here. And positive 0.069, and I'm just comparing this thing, right? And this test statistic falls somewhere here, which is in my fail to reject region. And it's always framed in terms of the null. So I failed to reject the null. I'm finding support for the null hypothesis. And so we should not calibrate or recalibrate the machine. Alright, we're finding evidence in favor of the hypothesized value that indeed the average temperature is 142. Now if we rejected the null, right, if my test statistic was such that I'd be in the shaded region, then I reject the null in favor of the alternative and say that the average temperature is something different from 142. And on the left-hand side, it would be something less than 142, and on the right, it would be something greater than. Let me go back to the question, see if I've answered everything. Yeah. And so that is the answer. The one other way that you could do this is to take your t-stat, okay, take your t-stat value, which is this 153, negative 1.53 rather, and find the associated p-value for a two-tailed test. Now, we can't look at a table for the p-value, but we can use Excel. If I use the formula called t-dist, alright, I simply plug in the x value as the value of my t-stat, degrees of freedom, 23, and tails, this is a two-tail test. Oops. I've discovered the error there. When I input my test statistic, I have to put the absolute value in. Okay, so the absolute value. And then you put the number of tails too. And so if you do that, so 1.534, 23 degrees of freedom, 2 tails, this is your p-value. For the two-tail test, right? And since this p-value is greater than alpha, we fail to reject the null. If the p-value had been less than alpha or equal to alpha, then you reject the null. But we certainly fail to reject.